The American physicist John Wheeler rather likes this kind of scheme because I think the idea is that he hopes that when everything does this bounce, the fundamental constants of nature might get all jumbled up and have a different value later on. This is the sort of thing that sometimes people like to have because there's an issue which worries physicists often, is the constants of nature seem, at least, to be kind of adjusted so that life can exist. And the question is, how did that happen? It's not very clear to me that that is the case. There are questions which come up. I don't really want to address that point here, apart from here, just on the slide. But what Wheeler was using this for was hoping that each cycle the constants might get jumbled up, and so most of these wouldn't have life in them, but if you happen to get all these constants having the right value, that's where we have to be, and that's why they're right. So that's a nice idea. The same idea was taken to more extremes by Lee Smolin. This is a really crazy scheme. And again, I should say that crazy is not a derogatory term. But in this scheme due to Lee Smolin, here we have different phases of the universe. Here there's these trumpets. They're not trumpets, they're meant to be histories of the universe. You imagine the time going in the direction of the trumpet, and going across you find the spatial universe, and every now and again it forms a black hole. This is a singular state where again the notions of space and time go crazy, and the idea is that this is the source of a new universe, and they keep sprouting off this way. Smolin also incorporates Wheeler's idea, and you want to have some kind of natural selection of universes. It's a wonderful idea. Whether you believe it is another matter. One of the reasons I worry about it is that the geometry is very hard to make sense of gluing one of these things up to the next from a geometrical point of view. And I should say all these people who look forward to these ideas are very respectable cosmologists. So again, I can say that the ideas are crazy without being derogatory. Here's another scheme, called the big splat sometimes. These are things called D-branes. D-branes are part of string theory. I'm not going to explain what D-branes are, partly because I never understood them myself. But they do require these extra dimensions, and these things sort of push out into the extra dimension in space-time, and as they collide here, they're supposed to be the source of the new universe. So that's the big splat. Or else it's referred to as the Aharonov model. The other models, one due to Penrose, which in some respects is the closest to the one that we described, but it is very different. This is also a string model, and then Steinhardt and Turok came back and produced a cyclic version of this thing here. But I don't want to say any more about these ideas, because I want to tell you my own crazy idea. And let me first, before doing crazy things, let me tell you about the standard cosmological models that Friedman introduced. I hope you can see this. I put it on the other side and they're bigger, but let me perhaps I should. Here we have the one we just looked at, just one cycle of the closed universe. The K here is curvature. So it's the curvature of space. Now you have to imagine that all these diagrams are space-time diagrams, and so time is going up the page, which will be the normal situation with my pictures, and you must think of sections through this represent the spatial universe of each time. So this model, the sections are all closed up, they look perhaps like circles edge on, but they really, you have to think of them as really three-dimensional spheres. That's hard to visualize. But there'll be something even more hard to visualize shortly, so don't worry too much about it now. Here the universe expands and comes back to this big crunch. These three spatial geometries, that's positively curved, zero curvature, negatively curved, I'd like to say something about them. In fact, perhaps I should go over around because these pictures, I think you ought to see it full size. These are pictures of the Dutch artist M.C. Escher. I should say this is actually a wooden model, but these are pictures. This is they're all tessellations of angels and devils, very cleverly done. Here we just have the infinite Euclidean plane. You have to imagine the pattern going on for infinity. It represents the flat Euclidean plane middle case here, sorry, let's go to the top one. The middle case here. This is the positively curved case, so that's just this case here. And this is what's called negative curvature, the hyperbolic universe is described. And I'll say a little bit more about that in a minute. But these are the three different kinds of spatial geometry. You've got to imagine it's really three-dimensional. I've only got flat versions of it. But Escher's pictures are very good representations of these three different geometries. Let me give you another picture of the bottom one, but I want to say the most about that. It doesn't mean that I think this is the actual situation of the universe. We don't know, I should say. It's very close to the flat one, but that, in a certain sense, is the worst possibility because it's just slightly one way or the other. It could be this or this, and we don't know which it is. It's close to that, but it could be any of the three, as far as present-day observations go. But let me show you this other Escher picture. It's also Escher, but this is a little bit nicer. It really tells you what the geometry looks like. Straight lines in this geometry are either diameters of the circle they went across, or else they are arcs of circles which meet the boundary at right angles. But the particular feature I want to tell you about here, well, first of all, that the whole universe, the whole infinite universe, and the negative curvature case, is represented inside this finite circle. That's very nice. You can represent the entire universe model as a finite region in the plane. But the other feature is that it's what's called conformal. It's a representation known as the Poincaré disk, perhaps for the reason that it was due to Beltrami. Of course, this is not an uncommon phenomenon in mathematics where the name is actually not the first person who found it. In this case, it's not so bad because Poincaré did in fact rediscover it. There are many cases where the name is actually the person who's named after didn't even know the result. But here we have the Beltrami conformal representation of the hyperbolic plane. When I say conformal, what does that mean? Well, that means that all the shapes, well, if you get small enough, notice that these fish, or whatever they are, as you get nearer to the edge, look as though they're a bit distorted, but the smaller the shape you look at, the less the distortion is. And in fact, the eyes, the circular eyes of these things, are still circles no matter how close to the edge you get. So if you think of the infinitesimal shapes, they are always the right shape in this representation. The closer you get to the edge, the more the compression is on the shape, but the compression is uniform in all directions. So that's what we mean by conformal representation, or another way of saying it is that angles in the actual geometry are correctly represented in the representation of the Euclidean plane. But the other feature is that the whole model is finitely represented. So you see, you can imagine if you were a Euclidean person, you could take a walk, and as you get near the edge, you could step over into this forbidden region on the outside. Of course, if you're one of the creatures living in this world, you try to step over, but then your feet get smaller, of course, and so you never make it. You just keep on walking and closer and closer to the edge. So we have that it's conformal, that's the first thing. And secondly, that infinity in this hyperbolic geometry is represented by this nice smooth boundary, which you could imagine going beyond into this other world out there outside the entire universe of this hyperbolic geometry. Okay, so that's the those are the three geometries, particularly the hyperbolic one. Now, what about the second law of thermodynamics? The second law of thermodynamics, not just the second law of thermodynamics, but the mystery of the second law. Now, what does the second law tell us? Well, it tells us, roughly speaking, that things get more and more random as time goes on, but things are getting worse and worse before we knew all that. That's no mystery. But there is a mystery, and I want to come to that, because that's really what I want to talk about. So I'm afraid, just about getting the birds on the slide there. There they are. I want to make a more detailed description of what this means. In fact, let me put this on outside, and this is awkward because it's upside down. So you excuse me, I'll keep putting them